Hello, Chem 1B. This is Chapter 14, Lecture Video 9, and we're going to be talking about reaction mechanisms in this video. So, reaction mechanisms are kind of new to your education in chemistry. Now, what they are is a step-by-step breakdown of how a reaction occurs. Now, normally when we look at a balanced equation or a chemical reaction that we're given, almost always those are what we call overall reactions. They kind of give you the before and after, not the path from point A to point B, right? So like kind of think of an analogy might be you starting your car, right? So when you start your car, what we see typically is we put the key into the ignition and we turn it and the car starts. But there are a lot more steps in between those two things, turn key, car start. We only really see turning the key and the car starts. That's kind of like an overall reaction. In reality, most reactions happen in a series of mechanistic steps, or what we'll learn are called elementary steps. And so that's what a mechanism is. Now, mechanisms can be predicted based on chemical kinetics, a lot of what we've been learning in this chapter. So we can make an educated guess of a rate law for a reaction based on a proposed, what we call a reaction mechanism. At the end of the day, however, that rate law that we can take a guess at has to be based on experimental data. Most of the time what we do is we determine the experimental rate law, and then from that rate law we can develop what we call a proposed reaction mechanism. Mechanisms, what they do is they really kind of provide a molecular picture of a reaction. Basically, hey, in the first step of the reaction, these two things collide and they react and form these products. And these products then go away to react again to form these products and so on. And it's really like we're breaking down the overall reaction into multiple smaller step reactions. It basically gives you the molecular viewpoint of the reaction, right? Reactions are where our reactants are colliding. Well, usually it's not just one collision that leads to the products at the very end of your overall reaction. Multiple steps are occurring. So a complete chemical reaction is going to usually happen through what we call intermediate reactions. And we have a special name for our intermediate reactions. They're known as elementary steps. These are reactions that are occurring in a single step. So literally these two things are going to collide with each other. Bonds are going to be broken, new bonds are going to be formed, and we're going to form these products. Now those products that we form in an elementary step usually are used in the next elementary step in a reaction mechanism. Now, one of the things about all reaction mechanisms is if you add up all the elementary steps, you absolutely have to get the overall reaction. Now, this doesn't really mean that the mechanism's correct. It just means that's just like a minimum qualification as far as whether or not we have a reaction mechanism or not for a given overall reaction. So using the rate law, we can write reaction mechanisms and predict how a reaction actually progresses at the molecular viewpoint. And this is where I kind of have to take back one little thing I said in like lecture video 3. In lecture video 3, I said you cannot use stoichiometric coefficients as the exponents in a rate law. Now, in that video, if you listen carefully, I said from an overall reaction. Overall reactions, we cannot use the stoichiometry to write our exponents for our experimental rate law. That just cannot happen. But we can do exactly that from an elementary step. So if we have a reaction that's an elementary step, we can use the stoichiometric coefficients in that reaction as the exponents in our rate law for that reaction, meaning we can directly write a rate law from an elementary step. At the end of the day, this rate law is not the answer. It's the answer for a single part of an overall reaction. And it might not even be true because the reaction mechanism might not be true, right? It's a proposed thing. It's not a for sure thing. So at the end of the day, the overall rate law of any reaction can never really be determined from a reaction mechanism. We can take a guess from a reaction mechanism, and we can get the proposed rate law from a reaction mechanism, but we can't get the actual rate law unless we do an experimental setup and we get experimental data and use that to determine our rate law. So let's look at a reaction mechanism so you can kind of see what I'm actually talking about here. This here is an overall reaction. And a proposed reaction mechanism for this overall reaction is going to happen in 2 steps. So we don't just have these 2 things colliding and forming those. That's just the kind of, this is the initial starting point, and this is the final point. We don't directly go from A to B here. That's not what's happening. In general, most reactions happen in multiple stages, and these stages we call elementary steps. So the first step in the proposed mechanism for this reaction is that N2O actually reacts with another N2O. This forms NO3 and NO. And through this first elementary step, we get stuff that's going to react in the second elementary step. In the second elementary step, this NO3 component that was formed here is now going to be used up here by reacting with the CO also in the reaction container. And this forms these products. Now, if, like I said earlier, we add up all the elementary steps in our reaction mechanism, we absolutely have to get back the overall reaction. And that's, again, that doesn't mean that our reaction mechanism is correct. That's a bare minimum qualification. So let's look at what happens when we add these 2. If you add these 2 reactions, you can see that the NO3s are going to cancel out, and one of the NO2s on the reactant side is going to cancel out with the other one on the product side. And what we're left with is this guy plus this goes to this plus this, which is exactly our overall reaction we started with. This is, again, not really an indication that our mechanism is correct, more so just, hey, it's a possible mechanism. NO3 is kind of special here. It's what's known as a reaction intermediate, and we'll get into this in a bit. NO3 in this reaction mechanism is the only substance that doesn't actually show up in our overall reaction. And they're kind of a special part of reaction mechanisms. Before we get into defining a reaction intermediate, let's talk about writing rate laws directly from elementary steps. Like I said, in general, we can write a rate law of an elementary step directly from the balanced chemical equation using the stoichiometry as the exponents in our reaction. Now, you need to be able to do really 3 things here for any elementary step. You need to be able to determine what we call the molecularity. You need to be able to write a rate law, and you need to be able to determine the order of the reaction. So molecularity is really the number of reactant molecules present in the elementary step. So in our first elementary step in this picture, we have a single reactant, A, is breaking apart, forming products. This is what we call a unimolecular elementary step, meaning a single molecule is in the reactant side of our reaction. There is only one type of unimolecular elementary step. It's a single reactant breaking down into multiple products. The rate law of this would simply be, hey, this is our reactant. It has one thing there. So our rate law is rate is equal to K times our concentration of A, technically, to the power of 1. Again, we don't show the 1 because not showing it's the same thing as showing it. And since there is an exponent of 1 here, our overall order of this reaction is simply a first order reaction. It's a first order elementary step with a unimolecularity. The second reaction is one of two possible bimolecular, right? Bimolecular reactions occur when we have an elementary step with two reactants present in the reaction. Now, this can be where we have two of the same reactant, A plus A. In other words, this is 2A goes to products, right? We're just writing it out as two separate A's so that you can kind of see it's two molecules that are reacting with each other. And in this scenario, we have rate is equal to K times A squared. Again, we're pulling the 2 here directly from the stoichiometric coefficient in our reaction. And really, A plus A is 2A. This would give us a second order reaction. The other bimolecular is where we have A plus another different reactant, B. So we have two different molecules reacting with each other, going to products. It's still composed of two reactant molecules. Our rate law is going to be K times A times B, all to the power of 1. But overall order is still going to be 2 here. The last type of molecularity that we typically see, and these are the most rare, is termolecular elementary steps. And that's where you have 3 molecules in one reaction on the reactant side. You can have 3 different kinds, right? Where we have 3 all of the same element or all of the same molecule reacting with each other. This gives us a rate law of K times A to the power of 3, and it's a third order reaction. Or you could have a termolecular elementary step where you have 2 of the same molecule reacting with 1 different molecule. You'd get K times A squared times B, which again still gives us a third order rate law or elementary step. And finally, the last termolecular is where we have 3 different molecules all reacting with each other, and we'd get this rate law. Rate is equal to K times A times B times C concentration, and our order is still to the power of 3. Again, I can't stress this enough. We can only write these rate laws directly from these reactions due to the fact that they are elementary steps. If this was an overall reaction, we would not be okay to write the rate law directly from that information. So, how do we determine an overall reactions rate law from a reaction mechanism? We can kind of do it. We can at least come up with a proposed rate law for an overall reaction if we know the reaction mechanism. And the way I like to think about this is typically based on a relay race. If you've ever run a relay race, you know, or seen one, you know that the next person in the relay can't start running or swimming until they get the baton. And this is true of reaction mechanisms as well. We can't start the second reaction in our reaction mechanism without the first reaction having already happened. And if you know anything, I used to run track and I coached track for a while. If you know anything about relay races, a lot of people mistakenly think that the person with the relay team with the fastest athlete is going to be the one to win. And that's actually not true. It's the relay team with their slowest runner is actually faster than the other relay team's slowest runner, because they're going to delay the baton handoff, right? Whoever's your slowest athlete, they're going to determine whether you win or lose the relay race in most cases, because your really slowest guy is going to be competing against the other team's slowest guy at the end of the day, because that's what's going to delay the handoff most of the baton. And that's also true of our reaction mechanisms. When we want to write a rate law for a reaction mechanism, we have to look at what we call the rate determining step. In other words, the slowest elementary step is going to limit the rate of everything else in the reaction. And because of that, our overall rate law is always going to be based primarily on the slowest elementary step, or in other words, what we call the rate determining step. So it's the one that governs the overall rate law for the entire reaction. So let's define some other stuff here. A reaction intermediate is something that appears in an elementary reaction as a product initially, but then in a later elementary step is a reactant and gets used up. Reaction intermediates do not appear in the overall chemical equation. Let's talk about catalysts a little bit too here. They are something that usually speed up a reaction. A catalyst generally will appear in an elementary step as a reactant initially, but is formed again as a product in a later elementary step. Catalysts also do not show up in the overall chemical equation. So let's do a problem. Let's say we have this reaction mechanism. We have the same one that we just saw, right? For the reaction of NO2 reacting with CO going to NO plus CO2. All right, this reaction that we saw earlier is the overall reaction here. And these are our reaction mechanisms that we saw in the previous slide. But now I'm telling you, hey, the first step is slow. What that means is I can now determine or propose a rate law for this overall reaction based on this reaction mechanism. Again, we care about the slow step as our rate law for the overall reaction because it's the one that limits the speed of the entire process. So what is the rate law for this reaction? Well, rate is going to be equal to K times the concentration of NO2 squared. This is going to be my rate law for the overall reaction. And the reason why is because this is the rate law I can come up with from the slow step. Remember, rate laws always only depend on our reactants. And we have two NO2s in that reaction, i.e. I'm getting this exponent of 2 from the stoichiometry in this elementary step. Again, rate is always going to depend on the rate limiting or rate determining step, the slow step. So because of that, our rate law for the overall reaction, also for our first step, but because the first step is slow, they are going to be equal to each other, is going to be rate is equal to K times the concentration of NO2 squared. And so that is the end of this first lecture video. We have two different types of problems we're going to see here, where one is the slow step is first in our reaction mechanism, which is, to be fair, the easier of the two, as you might have guessed, just based on how easy this problem was. And then the other type of problem we might see with this is where the slow step is second, and that complicates things significantly. So we'll do that in the last lecture video of this chapter. Again, if you have any questions, as always, please come to my discussion sessions or email me.